Okay, we are now up to Chapter 7, Linear and Second Degree Equations. As I've said before, the material builds on itself. A lot of the information you're going to see in this section, in this chapter, builds on the previous chapters. We just look at them a little differently as we add more terms into the mix. So we're going to be looking at linear equations, identifying them and solving them. Going to bring in second degree equations and then the applications, and those are the electronic applications that we see as we start moving closer and closer to applications specific for this course. So we're going to recognize and identify the parts of an equation. We're going to do some solutions, give you opportunities to use your calculator, apply the rules that have been developed in the first 6 chapters of the text, and then learn to verify the solutions to equations that have been solved. Your text covers that pretty extensively as it introduces a solution. It also encourages you to verify them accordingly. So in looking at linear equations, they're algebraic expressions separated by an equal sign. That's why we call them equations. Equals, equations. The equal sign implies that the expressions are in fact equal. So if we look at the example here, solving for the unknown, and that's typical in these types of math expressions, you're solving for the unknown. There might be one unknown, there might be two, there might be more. In this case, we have one unknown. It's the x. So 16 plus x equals 20. All we need to do is figure out a way to isolate that x to the other side, the right side of the equation, and the solution for x will essentially fall out. So in this case, if we subtract 16 from both sides, we end up with x equal to 20 minus 16, and x equals 4. So that one is pretty simple. If you want to verify, take the 4 value, stick it back in for x, and make sure that on both sides you have an equation. One side equals the other. Rule 7.1 says we can perform any mathematical operation on one side of an equation provided we perform the same operation on the other side. And most of what we're going to be doing is that exactly. We will be applying Rule 7.1. The rule means that we can make any change we want to in the value of one side as long as we also make the same change on the other side. So if we roll back a slide, that's exactly what we did in this preliminary solution. We subtracted 16 from both sides, and we're able to solve for x. The next rule says to solve for both linear and second degree equations, there's a 5-step process. First, clear any fractions from the expressions. 2, move all terms containing an unknown to one side and combine them into one term. It's usually preferable to move the unknowns to the left side of the equation. Move all constants to the other side and combine terms. Step 4, perform the operation or operations necessary to make the coefficient of the unknown equal to 1. Don't forget to perform this operation again on both sides. So again, this is what we've seen before as we're building our math skills. Finally, step 5, substitute the value of the unknown back into the original equation to verify the solution. Rule 7.3, terms may be moved from one side of an equation to the other by changing their signs. So if we look at this example, 4x equals 20, we're going to solve for the unknown x. So to do this, instead of subtracting or adding to both sides, we're going to divide both sides by that value of 4 that we have on the left side of the equation. In doing so, 4 over 4 is 1, so that in essence becomes x, and then 20 over 4 means we're going to divide 20 by 4, and it gives us the value of 5. So if we stick it back in the relationship, 4 times 5 equals 20, bingo, we've got an equality. Cross multiplication is another way of solving linear equations. In cross multiplication, it becomes a shortcut of multiplying or dividing the terms in order to simplify terms. This becomes one of those operations or methods that you learn to do primarily by inspection. In essence, it means I can move the 4 out of the denominator and into the numerator on the right side, and I can move the 1 out of the denominator and into the numerator on the left side. The implication there is multiplication. We have multiplied both sides by that value, or we have multiplied both sides by the given value. So in this case, x times 1 gives us x, 20 times 4 gives us 80, and we end up with a solution of x equal to 80. So it takes a little practice. It's one of those very helpful steps to help you reduce expressions and equations into a solvable format. So looking at another expression here, 20 divided by x equals 5. In this case, we've got to get the x out of the denominator and into the numerator so we can solve it. That's just by convention. You don't have to do it that way, but you will see that most solutions are that way. So in essence, I'm going to move the x to the other side of the expression and the implied 1 by the other side. This can be simply done by thinking in terms of just inverting both sides. It changes nothing as long as I do the same thing to both sides of the expression. So inverting 20x, I get x over 20. Inverting 5, I get 1 over 5, 1/5. So now what I need to do is I need to isolate the x to the left side of the expression. I do this by multiplying both sides by 20, and in doing so, I get the cancellation on the left side of the 20s, and I get 20 divided by 5 on the right side. So in doing this, I end up with x equal to 20/5, or 5 divided into 20, which goes 4 times. So x equals 4. I can take that value, stick it back in the original expression. 20 divided by 4 gives me 5. Okay, or I can divide both sides by x. Okay, so this is the same expression that we had in the previous slide, but in this case we're going to play with the x. So I'm going to multiply both sides of the expression times x. This in essence brings the x to the right side of the expression, and I end up then with the same relationship, because what I will do in the final step is I will divide 20 by 5 and get x, and I will get the answer of 4. Twice the sum of a number and 3 is 10. So we're going to just do a solution here, kind of a word problem. Twice the sum of the number and 3 is 10. So we're going to build an equality from that little word problem. So we're going to find the number. So in doing this, let x be the number, then 2 times the amount in parentheses, x plus 3 is 10, is the mathematical expression for that little word problem. So multiplying through, 2x plus 6 equals 10. We've simplified the expression. We're going to move the known values, the real values, to the right side of the expression. So I'm going to subtract 6 from both sides, 10 minus 6, and in doing so I get an intermediate step there of 2x equals 4, and then I can divide both sides by 2, and I get x equals 2. So I've solved then for the number 2. So twice the sum of a number, that number being 2, plus 3 is 10. So now the next logical step is to move into something called second-degree equations. Up to this point, we've solved equations by means of addition, subtraction, multiplication, or division. Some equations we use in electronics require additional operations. So to do this, we move beyond the 4 operators, addition, subtraction, multiplication, division, and we move into some special functions. In this case, we're going to employ the power of squaring a number or taking the square root of a number for us to solve an expression. So if we have an example like x squared equals 81, what we have to do to both sides of the expression is take the square root. The square root of a square gives us back just the number. The square root of a number, pull out your calculator and solve for it. So in this case, the square root of x squared equals the square root of 81. When we take that square root on both sides, we end up with a solution of x equals 9. A key point here, the square root of the number is that number itself. Sometimes it's nice and clean, like this. The problem has been set up. The author has picked a number that we get a quick answer for. A lot of these, again, you will be able to do by inspection as your skills in math continue to develop. So let's look at an example. Find x. Another fairly simple example here. But this one is instead of taking the square root of both sides, we're going to square both sides. So the square root of x equals 5 allows us to take the square root of the square of one side and the other to solve for the problem. So the square of the square root of x is equal to 5 squared in this case. In doing this, the radical is removed, and we end up with x equals 5 times 5, or 25. So these are fairly simple examples, but you get the idea. What you have to do is develop your skills in using squares and square roots by practice. In the applications, then, this is where we start looking at taking those things that are electronic in specific and applying them to some of these rules that we've developed. So often in electronics problem solving, we are solving an equation or solving for an unknown. You're going to see the author bringing up Ohm's Law over and over again because it's the most simple and fundamental relationship to help you build these skills. So you'll remember the little triangle, E, I, and R. In this case, we're solving E, the voltage, using values given to us for current and resistance. So in this case, we want to take the basic expression E equals I times R, but we want to solve for that I. So it's going to require us to do some manipulation and insert the values for 12 volts and 12 k ohms for the unknowns. So when we start with our fundamental expression E equals I times R, we're going to divide both sides by R. And what that does is it isolates the current I to the right side of the expression, and we have voltage over resistance then on the left. Very simply, you can move the values from one side to the other so that now I have I equals E over R. So doing that, the last step then is take the 12 volts, put it in the numerator, take the 12K, put it in the denominator, and solve. 12 over 12 gives us 1, and we've seen so far that we can take that value of K, move it into the numerator, K equals 10 to the minus 3. We can use the metric then, M, little m, for that value. So I, or the current, is equal to 1 milliamp in this expression. Using something a little more sophisticated, this is a typical transformer problem. The N equals the number of turns in the primary and the secondary in a transformer, and the values under the radical, ZP and ZS, is the impedance for the primary and the secondary. So we're given a basic equation here that sets up the number of turns in a transformer is equal to the square root of the ratio of the impedance, primary and secondary. So we're given values, the impedance in the secondary as 8 ohms, the number of turns in the primary 500, and the number of turns in the secondary 25. So the first thing we need to do is we need to massage our relationship here, because it has asked us to solve for the impedance in the primary, Z sub P. So we take our expression, And the first step is squaring both sides. We do this naturally because we want to get rid of that radical on the right side of the equation. So if I square the ratio of the number of turns and I square the square root of the ratio of the impedance, I end up with then the impedance by itself. This is good because that ZP is exactly what I want free and able to move around. So the ratio of the turns squared is equal to the ratio of the impedance. I'm going to multiply both sides by the secondary impedance in the numerators, and at this point I really do have the impedance of the primary free, and I could start putting values in this last step. But by convention, we move the right side to the left side to the right. If we do that, there's no sign changes, so it's just a clean operation that the impedance of the primary then is equal to the ratio of the number of turns, primary and secondary squared, times the impedance of the secondary. Plugging in our numbers then, 525, you can at this point do the math, 25 into 500, and then square it, multiply it times 8 ohms. You get an impedance in the primary of 3.2 k ohms. So this might look a little foreign to you to start with, and it seems like it might be a little complicated, but it's really not. You know, it's just like I told you in class the other day. How do you eat an elephant? One bite at a time. So, Chapter 7, we looked at linear expressions and second degree and some applications.